Hello everyone, welcome to lecture 7 in the series of lectures on programming fundamentals. So today's topic is data representation. It's a crucial topic for programmers, software engineers and computer scientists because we need to understand how a computer program sees the data, right? How the data is identified by a computer program and how is it stored in a computer, right? And how a computer program can work with different types of data. So that's the topic of today's lesson. Let's look at the outline. Here is the outline of the lecture. So the lecture is on data representation. First, we'll look at the terminology of data representation. Then we'll look at different units of data, and we'll then talk about number systems. Afterwards, we'll be talking about conversion from one number system to other number systems, right? How we switch between them. Then we will talk about representation of numeric data, firstly integers and then non-integers, and then also we'll be talking about non-numeric data. Let's get started with the first part of the lecture. In the first part, we'll be talking about terminology and units of data. Let's talk about data and information. So the task of a computer is typically to convert or to produce information from data. Right? Computers can just store data and provide the data when you require the data. The computers can also process data and provide you with information. One thing to note is that information can serve as data for a new process, right? So there can be a process after this information step that can produce that into a new process, right? For that new process, data is the information from the previous process, right? So one process's information is another process's data. Data or information. When I say data or information, it basically means these are interchangeable terms, right? So as I said earlier, information could be data for a new process, right? Information derived from one process could be data for a new process, and this data information is stored and they are retrieved when required and used. So when we talk about storing and retrieving data, we have to talk about units of data. So in the machine level, at the end of the day, in the hardware, data has to be stored, right? And at the machine level, it's usually a presence of a voltage or the absence of a voltage, right? And that's typically like a on state or the off state of a switch, right? If there's a voltage, it's on. If there's no voltage, that's off, right? And yeah, so it's a two-state scenario, right? It's a binary scenario, right? Whether it's on or off. So computers are two-state devices. Basically 0, we can say it's the off state, and 1 could be the on state. And in the hardware level, 0 could be the 0 voltage and 1 could be maybe 5 voltage, right? So basically the idea is it's a two-state scenario that we are talking about. The smallest unit of representing data is referred to as a bit, right? The word bit comes from binary digit, right? It's kind of an abbreviation for binary digit. A sequence of 8 bits is referred to as a byte. Sometimes it's also called an octet, particularly in computer networking. So when we go from byte to kilobyte, the traditional definition is that 1024 bytes will become or will be called a kilobyte, right? 1024 is because that's 2 to the power 10. But there is a little confusion given the word kilo has another typical meaning. Think of a kilogram to start with. So a kilogram has 1000 or 10 to the power 3 grams. Similarly, one could say a kilobyte could have a kilobyte has 1000 bytes, right? 10 to the power 3. Or as we saw in the last slide, the traditional definition is 1024 bytes form 1 kilobyte. That 1024 comes from the fact that that's equal to 2 to the power 10, reflecting directly the binary nature of the data representation. So which one is correct and what's to be used, what is to be expected, that depends on the context. So particularly in the operating systems level, when you talk about more theoretical, more precise information about data representation, we talk about file sizes, memory size, we tend to use the 1024 definition of a kilobyte. However, when we talk about disk capacities, particularly in, let's say, in the sales scenario, right, sales and marketing, it's very common to refer to 1 gigabyte equals 1000 kilobytes, sorry, 1000 megabytes, right? So if you buy a disk that claims to have 500 GB capacity, and if you plug it into a computer, you might find that it actually has a little bit less than 500 GB. It could be like 499 point something. That's because when it's branded, it's using the 10 to the power 3 definition, but in the OS level, of course, it's using 1024 definition. So there is some ambiguity in this. So we don't want ambiguous units, right? And the purpose of standardization is to overcome these ambiguities. So we want unambiguous units to represent data. So the standardization bodies like ISO, IEC, they proposed a solution to this. So the SI prefix, like I said, in kilograms, there's a meaning when we say kilogram, right? Kilometer is 1000 meters. Kilogram is 1000 grams. So kilo has a meaning. It's 1000 to the power 3. So the ISO standard specifies that 1 kilobyte is 10 to the power 3 bytes. 10 to the power 6 bytes is a megabyte, or 10 to the power 3, 1000 kilobytes is a megabyte. 10 to the power 9 bytes is a gigabyte, or 1000 megabytes is a gigabyte. So that's the SI prefix, right? So it goes in line with other SI prefixes like kilometer, kilogram, mega. Binary prefix, now that's referring to the OS, or the binary view of data representation, right, in the powers of 2 to the power 10, right? So 2 to the power 10 bytes is 1 kibibyte, not kilobyte, it's kibibyte, KIB. Then 2 to the power 20 bytes is 1 megabyte. And 2 to the power 30 bytes is 1 gigabyte. So 10 to the power 10 megabyte bytes is 1 gigabyte. Right? So that's what the ISO is specified as the standard, but still unfortunately people ignore this part and still keep using this kilobyte to mean 1024. However, that's not the ISO standard. This also marks the end of the first part of this lecture. Let's start part 2 of this lecture. Here we will be talking about number systems and conversions among different number systems. Let's talk about the two main types of data representations, which are the numeric data and the non-numeric data. Numeric data is quantitative, right? We are talking about quantities like number of students, marks for a certain module, or your GPA, right? So these are quantifiable. You can add the number of students from one course with another course, right? We can compare which course has more students. We can calculate the average number of students over a number of modules, right? So we can also do the similar things with the marks of certain modules and also GPA. So these are numeric data, right? They are quantifiable, and certain operations can be defined on that. Then we have non-numeric data. The most common non-numeric data type is text data. So we have given some examples like names, NIC numbers and registration numbers, addresses, phone numbers. So although these NIC numbers, registration numbers and phone numbers they contain numbers, we treat them as non-numeric data because operations like addition, subtraction, averaging do not have any meaning to be defined on this data, right? Therefore, as data representations, we define them as non-numeric data. And the other forms of data beyond text data is image data, audio data, video data. These are all non-numeric data. Now let's look at number systems. A number system, or a system of numeration, is a set of numbers, each of which is represented by a symbol or a group of symbols in a consistent manner. Let's look at examples, starting with the most common one that we use, the decimal number system. Right, with 10 as the base, we count from 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10, again 11, 12, 13, 14, until 20, and then 21, 22, so 10 more until 30, like that, right? So that's why we say it's a base 10 is the decimal number system. That's the most commonly used one. Computers, on the other hand, commonly use the binary number system, where 2 is the base of the number system. What do we mean by the base of a number system? So it's also called the radix, and that's a critical feature of any number system, right? One number system differs from another by the base or the radix. The base is the number of different digits or symbols that can appear in that particular number system. For example, in the base 10 number system, the decimal number system, we have 10 different digits, right? 0 to 9. Let's look at different number systems, more commonly used number systems and their bases. So binary, as you know, its base is 2, which means it has two symbols which are 0 and 1. In the octal number system, we have the base of 8, meaning we have 8 symbols, so from 0 to 7. As you know, the decimal number system with base 10 has 0 to 9, 10 symbols. And then the hexadecimal number system, it's of base 16, having 16 symbols, so we have 0 to 9 and A to F. Let's analyze the decimal number system further, taking an example number. So let's take the number 4567 in base 10. So what does that mean? We have 4 thousands, then we have 5 hundreds, then we have 6 tenths, and then 7 ones, right? 4567. And the way we have selected the terms is that this is 10 to the power 0, that's 1, and terms with 10 to the power 1, that's 10, so 10 to the 10 into 6, then 10 to the power 2, next position, so that means hundreds, then next position is 10 to the power 3 thousands, right? So that's the analysis, that's the breakdown of a number in base 10. So as you already saw in the previous slide, there is a certain value for a digit based on its position in the number, right? So it can be written down as this. So the value of a digit at a given position is the digit into the base to the power position, right? So in the previous slide we saw the number to the furthest right had certain digit into, so its position 0, right? Base 10, 10 to the power 0 is 1. The one shifted to the left has position 1, right? So starting with 0, then second position is 1, so 10 to the power 1 is 10, so digit into 10. Like that, we can define the value of a certain digit based on its position and the base that we are working with. So let's look at an example how this weight associated with digit position works. So this number is 123. As described in the previous slide, so in each position the value is determined by the base, the position into the digit itself, right? So in the first position is actually, when we count in number systems, we count from 0. So right, what we see first is actually position 0. So here the number is 3 at position 0. So the base is 10, 10 to the power 0 into 3. 3 is the digit. So 10 to the power 0 is 1. So 3 into 1 is 3. In the position 1, right, so after 0 it's position 1, we have 2. 2 is the digit, and then we have base 10, position 1. Similarly, for position 2, right, 0, 1, 2, we have 1 into 10 to the power 2, because it's position 2, base 10, the digit is 1. So here is another example. This time we have a decimal point. Right? This is 512.49. So how do we understand this in base 10 means? Right? It's the same principle as before. Right? So this can be broken down into 500 plus 10 plus 2 plus 0.4 plus 0.09. Right? So 2 slides ago we had this expression, right? The value of a digit at a given point equals to the digit into the base to the power the position. So 5 is at position 2, right? It's 0, 1, 2. 2, 10 to the power 2 is 100, right? 5 into 10 to the power 2. 1 into 10 to the power 1, because it's position 1, 0, 1. Then 2 into position 0, right? 2 into 10 to the power 0. Plus, how do we handle the 0.4? 10 to the power minus 1. So positioning is now after the decimal point, right? To the right hand side of the decimal point, we count minus 1, minus 2. So it's 10 to the power minus 1 into 4. And for 0.09, it's 9 into 10 to the power minus 2. Right? So as you can see, it's the same principle as before, right? We start counting from here. This is 0. Whatever that's to the left of this, we say 1, 2. Whatever that's to the right of this, we say minus 1, minus 2. That's how we count the position. Otherwise, it's the same principle to count the value of each digit at a given position, right? Now let's look at a different example. This time it's in the binary number system. Now this is the number system that works in the computers, right? Unlike for us, it's the decimal system that we are quite familiar with. Internally, computers use the binary system. So the base or the radix of the binary number system is 2, and symbols are 0 and 1. In this number, so previously in the decimal case, we call this point the decimal point. Now the radix or the base is 2. Therefore, we call this not the decimal point, but the binary point. So this number, so the principle is exactly the same to calculate the value of this, right? The positional value of each bit is the same expression. So it's the bit at the given position into the base to the power of the position. So we start again counting. This is the 0 position, position 0, position 1, position 2, position 3. Right? This is 0, position 0, position minus 1, position minus 2. Starting with here, this is position 3, right? 1 into 2 to the power 3, position 3. 1 into 2 to the power 2, because it's position 2. 0 into 2 to the power 1, because it's position 1. 1 into 2 to the power 0, because it's position 0. This one, 0 into 2 to the power minus 1. This is position minus 1. And then this bit, 1 into 2 to the power minus 2, because it's at position minus 2. Now let's look at the octal number system, where the base or the radix is 8 and the symbols are 0, 1, 2, 3, 4, 5, 6 and 7. So it's very similar to the previous cases, right? So we have 475.01. So now it's the octal point. So this is position 1. Sorry, this is position 0, right? We start counting with 0. This is position 1 and 4 is at position 2. The 0 is at position minus 1. This is at This 1 is at position -2. Let's start. So here position 2, 4 into 8 to the power 2. This 7 is at position 1, 7 into 8 to the power 1. Again, this 8 comes from the base. Position 0, it's 5, 5 into 8 to the power 0. Position -1, 0, 0 into 8 into the power -1. And then this 1 is at position -2, 1 into 8 to the power -2. Okay, one more example in another number system, the hexadecimal number system. As we have mentioned before, the base is 16, right? And it's also called hex instead of just hexadecimal. And we have symbols 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then A, B, C, D, E, F. Simple A to F can also be used. It's again same principle, right? So we have this now. This point is called the hex point or the hexadecimal point. Position 0, position 1, position 2, position -1, position -2. I won't go through the whole thing, right? Let's look at the two extremes. So here the position 2, 1 into 16 to the power 2. This one is position -2, so C into 16 to the power -2, right? So C is actually value 12 in decimal terms. So that's how you get the value corresponding to a number in a given number system. Let's look at some more definitions. The MSB and LSB, most significant bit and the least significant bit. Right, so here is a binary number. As mentioned earlier, we start counting the positions like this. So right, the rightmost one is position 0, and then we have 1, 2, 3 up to 7. And as you remember, the positional value is determined by the whatever the number here into the base, in this case 2 to the power of the position, right? So here the base to the power position is 2 to the power 0. This one, the base to the power position is 2 to the power 7. So least significant bit, LSB, it has the least positional value in terms of base into position. The most significant bit has the highest position, position 7. Right? So the way we write numbers, the leftmost one is the most significant bit, the rightmost one is the least significant bit. As we have seen, the same value can be represented in different number systems in different ways, right? The same value can be represented in different number systems. That also means that we can make conversions from one number system to a different number system, right? So there's a number in a certain number system, let's say in binary. How does it look like in decimal? Or how does the same number look like in octal system? Or how does that number look like in hexadecimal system? So that's called the number-based conversion, right? Number-based conversion. We will now look at how to do certain conversions. Mainly our interesting conversion is decimal to binary and binary to decimal, including integers and fractions, right? Fractions mean decimals, right? This is mainly interesting because decimal numbers are what we as humans are quite familiar with. We are used to working with decimal numbers, and computers internally work in binary. So that's an obvious conversion that we have to learn. Beyond that, we have octal and hexadecimal. We'll look at those conversions as well. How can we convert a decimal number into a binary number? So in this example, we are looking at 11 in decimal. How can we convert into binary? The sequence of actions is quite simple. I'll go through the steps to convert 11 in decimal to binary. So you divide 11 by 2. The quotient is 5. The remainder is 1, right? So when you divide a number by 2 or any other number, we are left with a quotient and a remainder, right? Remainder is what's left with. Quotient is, so 2 to the 2 into 5 plus 1 is 11, right? So 5 is the quotient, 1 is the remainder. Okay, we are left with 5. Then we divide 5 again by 2. 2 because we are going to convert the number into binary. So when you do that, the quotient is 2, remainder is 1, right? Again, since we had 2, let's divide 2 by the base 2. We are left with the quotient 1, remainder now is 0. We are still left with a quotient 1. Then we have one more step. We divide the quotient by 2. Then we have a quotient of 0 and a remainder of 1. Right, so we kept dividing the number by 2, which is the base we are going to convert into, until we are left with the quotient 0. Now what we do is that we write down the binary number starting from here, which gives us 1011 in binary, right? So 11 in decimal is equal to 1011 in binary. So now let's look at how to convert a decimal number into binary, but in this case a fractional decimal. So 0.25 in decimal, how can we convert into a binary number? We follow a process that's a bit, it's parallel to the previous process, but it's in the opposite direction, right? So now we start with the decimal number. Instead of dividing it by 2, we multiply it by 2, right? So when you multiply 0.25 into 2, we have 0.50. We multiply it again, right? The result we multiply again by 2. 0.5 into 2 is 1.0. So we keep multiplying until we have 0 as the fraction, right? So to the right of the decimal point, we need to have 0. Until then, we keep multiplying the fraction by 2. Now we already have the result. What we do at this point is the opposite of what we did. So previously we wrote the number from bottom to top, right? But now we write it from top to bottom. So we have 0, 1. So 0.25 in decimal is equal to 0.01 in binary. Let's look at another example. This time it's an interesting number. So I represent 0.1, a decimal number in binary. So I'm not going to go through the process of converting it. Say exactly the same like before, right? Try it out yourself. You'll end up with this never-ending pattern of numbers. It's like 0, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, again 1, 1, 0, 0. It will go on. You probably remember there are numbers like this in decimal as well, right? If you divide 1 by 3, you have 0.3333 like that. It's also a never-ending pattern. So it's not a perfect representation. Just like 0.333 is the representation of 1 by 3, 0.1 in decimal, when you convert it to binary, we cannot perfectly represent it. Right? We have a repeating sequence. So this is a common problem in base conversions. So if you convert this number back, you might end up with slightly different number, right? Now let's look at the opposite direction, the conversion in the opposite direction. So how to convert a binary number into a decimal number. This is easier than the other way around, right? So from decimal to binary, we had to do some divisions. From binary to decimal, we are directly using the positional values of the number, of the binary number. Then we are just adding the positional values up for the whole binary number to get the decimal number. So what does that mean? So if you have a binary number b, how to get the corresponding decimal value? Let's see, let's say that m is the position of the most significant bit, which is the leftmost bit. N is the position of the least significant bit, the rightmost. In this case, we are assuming a fractional part, right? So that's why we have this minus. You remember, after the point, the binary point, just after the binary point, we have the position value of -1, second one -2, like that, right? And bi is the value of the bit in position I. Right? So bm is the value of the most significant bit, either 1 or 0, and I at position I, what's the value of the bit, like that, right? Right, it will be clearer if when we look at an example. Let's see in the next slide. So the example of converting a binary number, so this case 11101.01, this binary number to decimal. Right, we'll follow the recipe that we saw in the previous slide. So here is the number, right? 11101.01. It's a binary sequence of digits. Right, now let's write down the corresponding positional values. Right, so in position 0, 2 to the power 0, position 1, 2 to the 1, the most significant bit 2 to the power 4, then beyond the binary point we have 2 to the power -1, next 2 to the power -2. So these are the positional values. When you expand it, so 2 to the power 4 is 16, 2 to the power 3 is 8, like that, right? 2 to the power -1 is 0.5, 2 to the power -2 is 0.25. Right, basically what then we do is multiply this by this, plus multiply this by this, plus multiply this by this, plus multiply this by this, which is 0, plus multiply this by this, plus multiply this by this, which is again 0, plus multiply this by this. Right, just add it up. Let's see in the next slide how we add them up and what we get. Right, basically now we see the addition, right? The addition of those values I said earlier, 1 into 2 to the power 4, 1 into 2 to the power 3, like that. So we have the couple of zeros. This 0 is here, this 0 is here, so those two become 0. So add them up and you will end up with 29.25 in decimal. That's the converted value into decimal, which corresponds to this initial binary value. So irrespective of what base you start with and into what base you convert them, right? Irrespective of the exact base, the principles are exactly the same, right? Same as what we have covered for binary and decimal, the conversions between them. So decimal to octal, decimal to hexadecimal, and the reverse operations, these are exactly the same approach. Similar approach, you have to just adjust it for the base, right? Otherwise the principle is exactly the same. We have an example here. So convert 1234 in decimal into hexadecimal. See if you can get this value, right? So hexadecimal means we have to convert it into base 16, right? So 16 symbols. Try it out. Right, so converting from binary to octal, we can follow the same principle as before, tuned to the base, right? We can use the positional values and write them in octal and then add them up, right? So the positional values in theory could be written in octal and then just add them up, okay? But there's a shortcut, there's a trick which is much easier than that. So octal means base 8, binary means base 2. 8 is 2 to the power 3, right? 8 is 2 to the power 3. Using this, we can have this shortcut or the trick where we basically, when we start with the binary number, we can group this number into with a group of 3 bits, right? Group it into sequences of 3 bits. So this one we see here can be grouped like this, right? So this 100 100, then 010 010, then 11. Okay, same number, right? This is the grouping now. So each of these 3 bits, 3-bit numbers, we can write it in octal. So in this case we had a leading 0, but it's not really critical because 011 or 11, just it's the same thing, right? So 001 means in octal it's 1. 010 in octal means it's 2. 011 in octal means it's 3, right? So 321, that's the octal number, right? Base 8 number. So it's quite easy to do it like that, right? The other direction, from octal to binary. So how do we do that? It's exactly the reverse trick that we saw in the last slide, in the previous slide, right? Basically, if you have a number like this 278 in octal, how can we convert into binary? Each octal value in each position, we write it in binary in 3 bits, right? 6 becomes 110, 7 becomes 111, 2 becomes 010. Basically just concatenate this sequence. There you go, you have the binary value corresponding to this octal value, right? Now the conversions between hexadecimal and binary, right? It's quite similar to what we saw for octal and binary. Remember that hexadecimal, it's of base 16, binary is of base 2, right? So 16 equals 2 to the power 4. So in octal, since it was 2 to the power 3, we grouped into we made groups of 3 bits in octal. In the hexadecimal case, we make groups of 4 bits. That makes sense, right? Let's look at an example. So this binary value, how can we convert into it's the corresponding hexadecimal value? Group them, make groups of 4 bits each, and each of the 4-bit groups write the corresponding hex value, right? 0011 means 3 in hex, 1101 means D in hex, 1001 means 9 in hex. There you go. How do we do the reverse? Exactly like before, we just do the reverse operation. So converting 2AF, this hex value, how do we convert into binary? Each of these hex values, F, write it in 4 bits. A, write it in 4 bits, 1010. 2, write it in 4 bits, 0010. Just concatenate the sequence. There you go. You have the corresponding binary value for this hex value. Right, so up to now you know how to convert between different number systems, right? If you are given a binary number, how to get the corresponding decimal value or the octal value or the hex value. If you are given a decimal number, how to compute its binary counterpart or the octal value or the hex value, right? So for octal and hex values, how to convert them back and forth from and to binary, we found a shortcut. Given octal means 8, which is 2 to the power 3, and hex means 16, which is 2 to the power 4, right? Using those features, we even found a shortcut to generate or convert between binary to hex and vice versa, also binary to octal and the reverse. Next, we'll be looking at arithmetic operations, right? So addition, subtraction, things like that. One constraint is that all the numbers in the same in one operation should be in the same base, and yeah, we'll see in the next part. So with binary numbers, operations are exactly the same as with decimal numbers, right? And however, we have to pay attention to the constraint of the number of positions. We'll see more in the next part. Welcome back. This is the part 3 of lecture 7. We are going to look at the representation of integers. Okay, we are at this point of the lecture, right? Representation of numeric data, integers. Just a couple of other topics to go. When we talk about a representation of data, right? So we take a step back from integers. Before integers, we want to talk a bit about data. So data can be either numeric data or non-numeric data. And non-numeric means like text or things like images, video. And numeric data, we have either integers or non-integers, right? Integers can be signed, right? Can have a different meaning when it's having a minus sign, or when it's having like no sign, means it's positive. Unsigned, yeah, there's no such thing as signs. In the non-integer part, we are mainly talking about floating point numbers, right? So we have a fractional part, or like for example in the decimal system, we have decimal point and beyond, right? That's non-integers. In a computer, data is stored in memory, right? Or we can say it's stored in registers. Typically, a register is an array of locations where each location is storing 1 bit. So as we mentioned, computers are working with the binary number system, right? So it's storing bits. Each location has an on or off value. On meaning 1, off meaning 0, right? However, each register has a fixed size, right? So number of bits a register can hold is limited by the size of the register, and if it can hold a number of n bits, so we start counting at this position and 0 1 2 but and up to n minus 1, right? So n bits. If you have a register of n bits, the possible number of distinct data or distinct values is 2 to the power n, right? By looking at all the combinations of ones and zeros, we can have maximally 2 to the power n number of distinct values. Let's first consider positive integers. When we talk about integers, right, there can be negative integers and positive integers. When we work with positive integers, like in any positive number, we don't waste any time saying it's plus 100 plus 24, right? We just say 100 or 24. Like that, we don't waste any of the positions in the register to say it's positive, because by default, if we don't say it's negative, it's positive. So exactly like before, if we have a register with n positions, right, we can have 2 to the power n number of possible values in that register if those numbers are all positive integers. Positive integers are also referred to as unsigned integers because we don't care about the sign, right? It's positive. You don't need to have a sign in front of it. Okay, this is the number of integers. So if we have a 3-bit register, 2 to the power 3 is 8, right? We'll have 8 different numbers that we can store there. And you could think 0 0 0, okay, that's 0. Then we have 1 0 0, which is 1. Then we have 1 0 1 0, which is 2. Then we have 1 1 0, which is 3, like that, right? Then we have 1 0 0, which is 4. So you can try it out. So there are 2 to the power 3 if n is 3. Smallest integer that we can store is obviously 0, because when all 3 are 0, it's 0, right? We don't go negative because we are talking about positive integers. And the largest integer we can store is, so if you have 3 bits, it's 1 1 1, right? 1 1 1 is 7. So 2 to the power n minus 1. 2 to the power n is 8. 8 minus 1 is 7. So like that, the largest integer can also be determined when we know n. That's for positive integers or unsigned integers. I hope you still remember what a byte is, right? A byte is a number having 8 bits, right? So when we have a byte, what's the number of integers, number of positive integers that we can represent, right? Given 8 bits or a byte, we can represent 2 to the power 8 number of positive integers, which is 256. The smallest value is obviously 0 when all the 8 bits are 0. The largest value is 2 to the power n minus 1. So 2 to the power 8 is 256, minus 1 gives you 255. So where all the 8 bits are ones. That's the largest value that we can store given we have 1 byte. Now let's look at arithmetic operations with integers, right? First, let's look at the binary integer addition. So we are trying to add these two binary values. It's quite similar to what we do in decimal addition, right? So binary 0 plus binary 1 is 1. 1 plus 0 is 1, and 0 plus 0 is 0. like that, right? If there was 1 plus 1, then it's 1 0. It's like that, right? That's straightforward. So this is the answer for that in binary, right? That's quite straightforward, no surprises there. This is example number 2, still on unsigned integers, right? Positive binary integers. So we have again a couple of binary numbers that we would like to add. But now we have this more realistic scenario, just like in computers. We are given a fixed sized registers, right? We only have, in this case, 8-bit registers. We can store only 8 bits in a given register. So how would that work? So let's just count 1, 2, 3, 4, 5, 6. It has 6 bits. This has 1, 2, 3, 4, 5, 6, 7, and 8. This is an 8-bit number. This is a 6-bit number. So let's see how the addition can work. Yeah, so when you put a 6-bit number into a register with 8 bits, we have a couple of leading zeros, which does not change the value of this 6-bit integer, binary integer, right? The second number is 8 bits. Okay, we have it, right? So let's do the addition like before, like 0 plus 1 1, so like that. Here in this case we have a carry bit, right? So if 1 1 is 1 0, right? So we put 0 and there's a carry, so 1 goes here, then 1 1 1 is 1 1. If we put 1 here, then there's another one, so 1 1 is again 1 0, like that. We have an additional 1, right? We have a new bit. So this is the 9th bit, but the register is only 8 bits long. So when it's stored, this bit is unfortunately not stored. That's a big problem, right? This carry bit, it's not stored in the register. This is called overflow, because this number is not equal to this number, because there's a big difference, right? There's a missing most significant bit, right? So this error is called overflow, and it happens because of the limited size of the registers that we have to work with. So certain systems can give an overflow error, certain systems might not, right? So you have to understand how each system works when you are working at that level. Up to now we looked at unsigned integers. So unsigned integers are by default positive. Signed integers, on the other hand, can be either positive or negative, right? It has a way for us to know that if it is positive or negative. There are different types of signed integers. Computers more commonly use what we call 2's complement method to represent signed integers. So there are several ways of representing signed integers, and the exact definitions are actually based on the word size or the number of bit positions. In the next few slides, we will try to understand what 2's complement method is and how to use it. Here is the positional values of bits in the 2's complement method. So for a string, or say a binary number of n bits, if it is 2's complement, if you start from the right hand side, the least significant bit side, this looks just like before, right? The first position, it's the 0-bit position. The weight is 1. It's because 2 to the power 0, that's the weight. So position number 1, 2 to the power 1 is 2. Position number 2, 2 to the power 2 is 4. Like that, it goes up to until the very end, but 1 before the end, right? So if it's n, if it's an n bit long number, if we start counting from 0, the last one is n minus 1. The one before last is n minus 2, right? So until n minus 2, we have the positional values determined by 2 to the power n minus 2. So this is the same as before. However, the last bit, so the most significant bit, the MSB, we have a different scenario. For the n minus 1 position, the MSB position, the value, the positional value of the bit is minus 2 to the power n minus 1. So that's a critical point. Remember, this determines the overall value, right? So this also determines if the number is positive or negative, right? So MSB determines the sign. If it is 0, the integer is either positive or even 0. If it is 1, the integer is negative. We'll see how this works in action in the next few slides. Given a binary number, an n-bit integer in 2's complement, how can we determine its value? So here is the formula to calculate it. It uses the positional values that we looked at earlier, right? This is the most significant bit. We saw that the positional value of the most significant bit is minus 2 to the power n minus 1. For an n-bit integer, the position of the most significant bit is n minus 1. The positional value is minus 2 to the power n minus 1. You multiply it by b n minus 1, which is this bit, right? If it is 0, this whole part is 0. If it is 1, this part is minus 2 to the power n minus 1. That's the most significant bit. The rest of the bits are here, right, from n minus 2 until 0, right, 0 to n minus 2. Each of the positional values are as before, 2 to the power I being the position. Then each bit you have to multiply the positional value of that position into the value of that bit in that position, right? That's what bi stand for. So here for b2, it's b2 into 2 to the power 2. Like that, you sum it up for all the bits. That's how you get this part. So as I said, if it's a positive value, this part is 0, then you are left with these numbers, this sum, right? This is exactly like before, the unsigned numbers. If it's a negative value, then we have some positive value here minus this value. You are left with some negative number. So that's the negative value of this. Oh, that's the value of it if it's a negative number. Let's look at what the smallest integer we can display or show, and what's the largest integer that we can show with this notation or with 2's complement for an n-bit integer. So smallest integer is the most negative number we can have. For that, this part has to be the most negative, this part has to be the least positive, right? The least positive one we can have here is 0. The most negative one obviously we can have is, if we just keep b1, then we have minus 2 to the power n minus 1. So the largest value, smallest integer, the most negative integer we can have is minus 2 to the power n minus 1, where this part only goes into determining the value, right? This part is 0. That's the smallest or the most negative, right? MSB is 1, this is 1, everything else is 0. The largest integer is the biggest positive number. Then this bit has to be 0, right? Then there will be no negativeness involved. This we keep 0, and then this is the maximum, where then every b is 1, right? Then it adds up to the largest positive value. The largest positive integer is 2 to the power n minus 1 minus 1. This is similar to the unsigned number scenario, right? 2 to the power n minus 1 minus 1. It will be clearer how to get the value of a 2's complement number when you look at these examples. So let's consider a 2's complement number where n is 4, right? N is 4 means you have a 4-bit 2's complement number. First, look at the scenario where we have positive numbers, right? This column, we have the most significant bit as 0. Then the corresponding values are very similar to what we had during the section where we discussed unsigned values, right? So all the zeros correspond to 0. 0, 0, 1, we have 1 because the value of the positional value of this is so this is position 0. 2 to the power 0 is 1, so we have 1 into 1, 0. In this case, we have position 0, we have 0. Position 1, we have a 1. Position 1, the value is 2 to the power, let me write it down. So the value here is at position 1, it's 2 to the power 1, which is equal to 2, right? So 1 into 2 to the power 1, that's 2. Here we have, so now 2 values. We have 1 into 2 to the power 1, that's this. And the next one we have plus 1 into 2 to the power 0. So this is 1, this is 2. So 2 plus 1, we have 3. Like that, you can work it out, right? Work it out for all these. So we have 1, 1, 1 at the end. We have 7. Okay. Let's look at the new scenario. I'll use a different color for that. We have now the 2's complement negative values. As you remember, this bit has a positional value of what? Minus 2 to the power n minus 1. So here n is 4. This is equal to minus 2 to the power 3, which is minus 8, right? That's how we get this value. Everything else is 0, right? So since we have a 1 here, so into 1. If this was 0 like here, right, it would have been 0, but here in this case we have minus 8. Let's look at other scenarios. So this bit at every line, it still stands for minus 8. However, this part has a different way to get values, right? So here we already saw it. That value is 1. So minus 8 plus 1 gives you minus 7. Minus 8 plus 2 gives you minus 6. That's what we saw in the previous slide in the formula, right? This determines a negative value and this part determines a positive value. When you add them up, you get the actual number this 2's complement number stands for, right? That like that 1 1 1 0 is minus 2. When everything is 1, so we have here minus 7, right? This part is minus 7, and this part is minus 8. Sorry, this part is plus 7, right? Plus 7. This part is minus 8, so minus 8 plus 7 is minus 1. So understand that. Let me erase this. So understand how it relates to the formula we saw earlier, right? So the most significant bit determines the negativeness, right? If it is 0, it's the same as the unsigned scenario we saw earlier, right? So the last n minus 1 bits determine the value. We take the position values, add them up. If the most significant bit is 1, it stands for a special negative value, right? Minus 2 to the power n minus 1. And you add those two together, the minus value and the positive value, then you have the value, total value of the string or the binary number, n-bit binary number. Let's look at the extreme values or special values. When everything is 0, we have 0. That's not a surprise. When we have, so the most significant bit is 0, we have the highest positive value where everything else is 1, right? This stands for plus 7. When the most significant bit is 1 and everything else is 0, we have the smallest value, the most negative value. It's minus 8. This is as low as it can get. So once you have the other numbers not 0, we are adding a positive part to it, so it becomes less negative, right? So starting with minus 8, it becomes minus 7, minus 6, and the value here is when everything is 1, we have minus 1. So as you can see, this covers a range of values starting from the lowest end minus 8, it goes on, then we have 0 at some point, goes on until plus 7, right? So this is the range. We can write it like this actually, from minus 8 to plus 7, including those two values. This is the range of values that we can write using a 4-bit 2's complement number, binary number. Let's look at another example. So the principle is the same, but now we have a different size, different n. N is now 8, right? Okay, so 0 doesn't change, it's just the number of zeros, right? It's just 1 0, 100 zeros, it's still 0. However, the other ranges change, right? The smallest one, can you guess? So if we remember from the last slide and the slide before that, right? The smallest integer we will get using the most significant bit that has a positional value of minus 2 to the power n minus 1, which is, so n is 8, n minus 1 is 7, so this is minus 2 to the power 7, which is minus 128, right? That should be clear, right? So everything else is 0, only the most significant bit is 1, right? Okay, there you go. The largest integer is when the most significant bit is 0 and everything else is 1. We have 2 to the power n minus 1 minus 1, right? So this is 127 in decimal, right? This is the largest integer. This is the smallest one, right? So the range is from minus 128 to positive 127. So the reason we have this minus 1, I'll use a different color, this minus 1. Do you remember in the unsigned scenario for a 3-bit, so in the unsigned case, unsigned, I'll write US, and let's say for a 3-bit, so n equals 3, the largest number we can write as 111, right? This is 2, this is 7 in decimal, right? So this value is obtained from 2 to the power 3 minus 1, right? 2 to the power 3 is equal to 8. 8 minus 1 is 7. So for a 3-bit binary value, the largest number that we can get is 2 to the power 3 minus 1. right? That's where we get this minus. It's the same minus here, right? So notice the differences in the unsigned situation where n equals 8, right? So in the unsigned case, when n equals 8, the largest number we can have is unsigned again. So I'll keep this part for unsigned, right? I'll erase the examples. Okay. So in the unsigned case, we have for n equals 8 unsigned. For n equals 8, we have the largest value is n to the power, sorry, 2 to the power 8 minus 1. 2 to the power 8 is 256 minus 1 equals 255. Smallest is obviously 0, right? So for the unsigned situation with 8 bits, we have 0 to 255. In the 2's complement, it's a signed representation. We have minus 128 to, so it goes through 0 until plus 127, right? This is the range here, this is the range there. So if you count the number of values, this has, including 0, 256 values it can give us, right? It can be stored, it can be used to show 256 values, right? 0 to 255. Here in the 2's complement, we have 1 minus 128 to plus 127. That's also, if you take the number of values, it's 256. So the number of values we can show are the same, but the range is different. So keep that in mind. That's the core idea of 2's complement. So how can we write the 2's complement of a given number? Let's look at an example. That's the best way to understand this, right? Okay, so let d be a positive decimal integer. So for example, 6 in base 10. How to get the 2's complement b of minus d, right? So now we are trying to find the 2's complement of minus d, right? So minus d is minus 6, b is equal to b. How to get this? That's the question. There's a sequence of steps which are not difficult to follow. First step is to determine how many bits we need. So the rule of thumb, you will realize why it is the case, is to use 1 bit more than what we want when we write the positive number in binary. What does that mean? So the positive number is 6. This is equal to, in binary, 1 1 0, right? In binary. So here we need 3 bits, right? So we want 3 plus 1 bits to write the 2's complement. You will see why. So we have n equals 4 because of this, right? So plus 1. So that is now sorted. What's next? So get b1 equals d in binary with most significant bit equals 0. So d is now 110 in binary, right? And so b1 is with the most significant bit, we add another 0. So that's where we needed the additional number, right? Additional bit. So that's 110 in binary with a new most significant bit, which is 0. So that's b1. So what's the next step? So n should be large enough, else increase n. So here we added the new bit. We didn't want to increase it further, right? This is enough. So n equals 0 is enough. Get b2, which is the ones complement of b1. Ones complement is simply flipping the bits. Whatever that's 0, make them into 1. Whatever that's 1, write them as 0. That's basically ones complement, right? So ones complement of 0, 1, 1, 0 in binary is 1, 0, 0, 1 in binary. That's the ones complement, which is now b2. Right, flip the bits of b1, then we get b2. That's easy. Finally, to get the 2's complement, b, we add 1 to b2. Right, so plus 1. Simple addition. 1 plus 1 is 1, 0. Okay. We carry 1 here. 1 plus 0 is 1. This 0 is now written as 0. This is still 1. This is the 2's complement of minus 6. So what did we do? To summarize, to get the 2's complement of any binary number d, we have to go through 2 steps. First step, complement or flip the bits, right? 0 to 1, 1s to 0s. And then second step, add 1. So it's quite a simple process to get the 2's complement of any given binary number. Let's look at another example. In this case, let's see how to write the 2's complement of minus 5. So n equals 4, it's given. Anyway, from the previous rule of thumb we said, so 5 is written as 1, 0, 1, right? So 3 bits. So we add another bit, then it becomes 4 bits. So yeah, plus 5 in binary in 4 bits is now 0, 1, 0, 1. Notice the MSB, the most significant bit, we have added 0. That's for plus 1, right? We need minus 1. So we have the 2's complement. First, we flip the bits. 0 becomes 1, 1 becomes 0, right? So 0, 1, 0, 1 becomes 1, 0, 1, 0. And then we add 1, which becomes 1, 0, 1, 1. That's the 2's complement of minus 5. It's important to note that the 2's complement that we obtain for a given number, it depends on the selection of n. So previously we saw how to write the 2's complement of minus 5 where n equals 4. So we can use a larger n than what's minimally required. So the minimum n should be 4, but a certain system might use a bit size, a number of bits of size n, as size 8, for example, or a 16 or 32, right? In that case, so in this case we have n equals 8. It will be different from when it was n equals 4. Let's see why. So plus 5 in binary in 8 bits is, so last 3 bits are the same, it's 1, 0, 1, but we have several leading zeros, right? So we don't need to add any more zeros. We are given that n equals 8, right? So if we take the 1's complement, we flip the zeros to 1 and we flip the 1's to be 0. So look, already it looks different. And then to get the 2's complement from the 1's complement, we add 1. Then it becomes this. So this is the 2's complement of minus 5 when n equals 8, which is different from n equals 4. That's an important point to consider. So just by looking at this number and the number from the previous slide, if you didn't know that it's an n equals 8 2's complement, it's not obvious that it's the same number, right? So when you specify 2's complement, we also need to specify the n, the number of bits. Otherwise, the answer will not be the same. Right. Let's see now how Python works with complements, negatives, negative binary numbers, right? Let's look at some examples. Right, let's see first this tilde operator. So 0 with tilde, what would it give us in Python? So it will give -1. So we are asking for the complement of 0, and what Python gives us is -1. So it's not exactly giving the 2's complement, right? It's a Python's version of complement, right? So tilde operator stands for complement. If we ask for complement of 0, it gives us -1. And if we get the complement of -1, maybe you can guess what the answer is. It's 0, right? It's just a reverse operation. So these are decimal numbers. Let's see. So if we ask the complement of 0 in binary, so bin means we are asking this argument to be converted into binary. Then Python has its way to show the base, this 0b. This 0b just says that we are now looking at a binary number. The number itself is 1 and the sign is here, right? We are now looking at binary number -1. So the complement of 0 is -1 in binary. What's the binary value of -2? So 0b stands for binary. Okay, we are not talking about a binary number. 10 is 2 in binary. Then we have the sign. So basically, we are now just converting -2 decimal into -2 binary. And yeah, 0b stands for binary, minus is there, and 10 is 2. In this part, which is part 4 of this lecture, we will be looking at the representation of numeric data, but now non-integers. When we talk about non-integers, we mainly refer to real numbers. So we are talking about numbers which are not integers. Right? In the computing context, these are typically floating point numbers. So mathematically, probably you remember, real numbers can be rational or irrational, right? Some of these numbers, for example, if you want to write down the decimal version of 1/3, right? It's 0.33333. It's an infinitely long decimal points, set of decimal points. So that's a real number, right? I mean, you can also have something like 0.75, right? So what is this floating point? This refers to the radix, right? The point that we use for decimal point. The position of this decimal point is not fixed, right? We don't say it's always a number with 2 decimal points or 3 decimal points, right? Depending on the number, that can have a variable amount of decimal points, right? So the radix can move around. That's why it's called a floating point as opposed to a fixed point, right? So in a fixed point, the number of digits after the radix point is predetermined. So floating point numbers which are very common in the computing context, is a way to represent approximations of real numbers, right? It cannot always represent the absolute value or the perfect value of a real number. For example, 1/3. It cannot show the perfect value, so it will work with approximations of these representations of real numbers. We talked about certain approximation happening when we use the floating point representation. The best way to understand is to look for a couple of examples. So let's say we have this number 123,450. That's one example. And the another one, okay, we'll look at the other one later. Right, this is the other one. 0.12345. Right? These are two very different numbers. First one doesn't even have a decimal point. The second one has 5 decimal point, 5 digits after the decimal point. Right. So what's the concept of approximating a number? So we would use a fixed number of significant digits, what we call the mantissa or the significand. So we will write the number in the form of a mantissa. So in this case 1.2345 into 10 to the power 5, right? So this part is the mantissa. 10 is the base and then 5 is the exponent. That's what we have written here. Right, we have exponent, base and mantissa. This is similar to the scientific notation of writing down numbers, right? Number equals mantissa into base to the power exponent, right? For a number having decimal points, so 0.12345, we can write mantissa 1.2345 into 10 to the power minus 1, right? The exponent is minus 1. So that's the idea. So here we have a fixed number of significant digits, right? That's the mantissa. So that's how you use this kind of notation to approximate numbers so that we can write them in the floating point representation. So in the last slide we said we can represent a number in the floating point format by writing the number in this form, right? So number equals mantissa into some base to the power some exponent. So different people can write their own mantissas for the same number, right? You can place the decimal point arbitrarily. So to reduce the arbitrary nature, to make it a bit more standardized, we have this widely used IEEE 754 standard. It basically has 3 fields. We will discuss these fields in the later slides. It will be clearer when we look at an example. Right, 1 bit for the sign to see if it is positive or negative. Then there's a few bits for the exponent. Then we have the mantissa, which represents some fraction, right? So it has an implied bit. You will see what this means later on. So if you look at single precision and double precision floating point formats, in single precision we have a bit sequence of 32 bits, right, to represent a number. In double precision we have 64 bits. In both cases we have 1 sign bit. For single precision we have 8 bits for the exponent and 23 for the mantissa. In the double precision we have 11 for the exponent and 52 bits for the mantissa. I invite you to read a bit more about IEEE 754 standards. There are some special cases like how we can denote 0. There's a concept of negative 0 and positive 0. So that's homework for you. Read about it and understand how it's done. Let's look at an example and see how we can formulate the floating point value according to IEEE 754. Right, this is the example number. So in decimal, we are looking at 0.15625. So from the techniques we already know, you can convert this into its equivalent binary form, which is 0.00101 in binary. So to get it into the required format, right, we are writing it down into the mantissa into base to the power exponent format. Right? So this part is equal to 1.012 into 2 to the power minus 3. Why is that? So we want to express this number such that there is only one bit left of the binary point. So binary point is here. We want to shift this binary point to this position, which is 1, 2, 3 positions. After doing that, we have 1.01 for the base in the base 2 into 2 to the power minus 3, because we shifted it 3 times to the right. So in single precision, we have something called the biasing. So biasing exists in both single precision and double precision. So in single precision, the bias is done by 127. So what does that mean? Exponent is biased by 127. So exponent is minus 3 here. We add 127. Then we are ending up with 124 in decimal, right? That is the biasing operation. So 124 in binary is this. That's 01111 in binary. So that's the biasing part of the exponent, right? You just add 127. The mantissa, or the fraction, right? It's called the fraction in the IEEE 754. We take this and we just drop this leading 1, right? This leading bit, because it's implied, right? So whatever the number we have, we will have a 1, and then we will shift the decimal point to the right of the first 1, and then we are ending up with 0.01 in binary, because this leading 1 is implied. Now I'm coming back to the homework. So what will happen if it is 0? Right? There's no leading 1. So what will happen to the mantissa and exponent? Right. So read about it. Try to figure it out. Okay, right. So mantissa, we have this leading bit implied. We just drop this, and we are ending up with this part only, which is 0.01 in binary. So we are left with this representation of this number. Sign bit is 0 because it's a positive number. Then we have the exponent, which is biased by 127, which is this value, right? 0.1111100. That's here. Then the fraction, or the mantissa, where the leading bit is implied, right? We are left with 0.1, 0.1, 0.0.0, so on. So that's the representation of this number in binary according to IEEE 754. Here are a few things you need to know about the representation of floating point numbers in Python. So floating point numbers, or floats in short, in Python, floats are double precision, right? So each of these values will require 53 bits. As we have seen, for example, 0.1, right? There are several decimal floats that are not perfectly represented as binary floats, right? It's not a perfect match when you convert it into binary, the decimal floats, some decimal floats. So how does Python work around it? So even though the values in binary are not perfectly matching the original decimal values, what Python does is that it approximates the binary floats, right? So the values entered or displayed are approximated by the binary floats, which are actually stored in the machine. And what Python does is it keeps the number of digits manageable by displaying rounded values, right? Instead of trying to make it perfect by showing as many numbers as possible, it can round these values so that you don't need to, you can manage with a less number of digits, right? So this is all about floats or floating point values in Python. Here is some more homework for you at the end of the part 4 of this lecture. This is regarding the approximations that we discussed, right? So if you open your Python console and try out this statement, right, it has to either return true or false, right? We are saying 0.1 plus 0.1 plus 0.1 equals 0.3. So it checks if these two sides are equal. If they're equal, it returns true. If they are not equal, it returns false. And if you try this out, the console, in the Python console, it will say it's false. Why is that? Think about what we have discussed so far and try to explain this observation. Another interesting observation, seems like a little contradiction, but this one it says false, but this one it says true. Why did that happen? How is it possible? And here also, right, we are on the left hand side we have 0.15 plus 0.15, so we know mathematically it's equal to 0.3, and on the right hand side we have 0.1 plus 0.2, that also using simple arithmetic we write 0.3, so it has to be equal, right? So when we have this greater than or equal to, it has to return true, but it returns false in the Python shell. Why is that? So remember what we discussed so far and try to explain these observations. That concludes part 4 of this lecture on representing numbers. Welcome to part 5 of lecture 7. We are going to look at the representation of non-numeric data. When we talk about non-numeric data, more often it's text data or textual data. However, it can be beyond that, where it could be audio files, videos, right, like multimedia. Now we will primarily look at textual data. So this would include letters, simple, capital, digits 0 to 9, symbols you have seen, right, the ampersand, exclamation mark, asterisk, and certain control characters you don't see them printed usually, but you see the effects, right, the escape characters, line fit characters, carriage return, things like that. Initially we talked about byte, a byte having 8 bits, right? So a binary number of 8 bits is able to represent 256 unique values, right? That comes from 2 to the power 8. So if we use a byte to represent non-numeric data, we can easily represent 256 characters if we map certain values of the binary numbers to different characters. So there are some standards that involve defining how these characters are mapped to different symbols. How these binary numbers, right, 8-bit binary numbers, how each of these 8-bit binary numbers are mapped to different characters. One popular standard, one of the early standards, is the ASCII standards. Stands for American Standard Code for Information Exchange. This was primarily for the Latin alphabet based languages. Right? That was also a big shortcoming because it did not provide any way to represent non-Latin based languages. Right? For singular Tamil, we cannot use ASCII. After some time, there was a new standard called the Extended Binary Coded Decimal Interchange Code to make a wider range of characters, but that did not become that popular. However, what we use currently widely is Unicode. So this supports several languages from that use different alphabets, different scripts, and for example, Sinhala and Tamil also is supported by Unicode. Let's first look at ASCII. So this is a widely spread standard that has been used for a long time, right? And mainly it covers upper and lowercase Latin letters, digits from 0 to 9, and punctuation. An ASCII code word has only 7 bits, which means there are 128 code words, right? So 2 to the power 7 is 128. Therefore, we have 128 standard ASCII code words. We said there are 128 ASCII code words, right? So numerically, we can order them from 0 to 127, the numeric value. But that does not say the value it actually codes for it 0 to 127, right? It codes for certain different symbols, right? So ASCII table is the one that shows us the mapping between the value of the code to what it's coding for, the code word, right? Right. For example, so we have starting from 0 to 63, right? So first column is decimal, second column is hex, third column is symbol. So this is a repetition of the same 3 columns, but so we are starting from 0 to 15, and then from 32 to 47 we have, and then 48 to 63 we have, and we see what kind of code words there are. The second column is just hex, right? So the decimal value we just represent in hex, right? So it's basically the same value. This is the symbol it codes for, right? So 0 codes for the null symbol. And look at the, so yeah, these ones are more the control symbols, and here we have things like the exclamation marks, quotation mark, right, dollar signs, whatever. And here an interesting bit, because so the numbers, the digits, the symbols that are coding for the digits 0 to 9 are here, and the value of the ASCII code is from 48 to 57, right? So note that. Here are some more ASCII table values, right? So here is the ASCII code word. This is what it codes for, right? So here are some other, so mainly we have the Latin alphabet characters. First we have the capital ones. So capital A is coded by value 65, right? Hex is now for 1. So here you can see up to capital Z we have 90, right? So contiguous set of values from 65 to 90 codes for the capital Latin alphabet characters. And see, we have the simple alphabetical characters again the Latin alphabet starting from 97. So this should be already clear to you that the code for a digit is not equal to the numeric value of the digit, right? We saw the examples, right? So the digit 1 is not represented by the code which has the value of 1, right? It was shifted somewhere else in the table. So note that, it's very important. The good thing about ASCII, since it has been like the most commonly used standard for a long time, it's supported by almost every computer. But as we saw, it only can support 128 symbols. The issue there is we have a lot of writing systems, right? Not just the Latin alphabet. We have Sinhala, Tamil. There are so many other languages which come with their own script, right? And ASCII cannot support all these types of different symbols, right? So then we need a better solution, something more broader than ASCII that can support all these characters. In order to overcome the limitation of ASCII, right? ASCII has only 128 characters. So that's a limitation. To overcome that limitation, Unicode was proposed. So Unicode has 32 bits. Each symbol has 32 bits. So in ASCII, we had 2 to the power 7 number of characters. In Unicode, we have 2 to the power 32, which is a very large number that can easily support all the different writing systems in the world. That includes mathematical symbols, different scientific symbols, right? And it still has space for future expansion, right? Not all the characters, right? Not all the 2 to the power 32 bit characters are taken, right? So if let's say suddenly a new writing system comes up, we can define we can allocate new characters from Unicode to those new symbols. Also note that the first 128 characters are exactly the same as the ASCII characters, right? It's a direct mapping, so it's directly compatible. So if you write something in let's say Sinhalese or Tamil using the script of Sinhalese or Tamil, right? So I'm not talking about the language, it's a script, right? The writing system. If you write something in one computer that uses Unicode, anywhere else in the world, if that computer uses Unicode, that's exactly replicated like that, the way you intended, right? Irrespective of the platform, irrespective of the program or the writing system, as long as you use Unicode, the same code used at different systems will show you the same character, will represent the same character, as long as all these different systems use Unicode. Let's take a quick note on writing systems. So writing system is not the same as language, right? So different languages might use the same writing system. So typically, so when it comes to the Latin alphabet, right, the Latin symbols, as you know, the English language uses the Latin symbols, the Latin alphabet. Spanish, so all this Southern America uses the Latin alphabet because most of these countries use either Portuguese or Spanish as their language, right? And both these languages use the Latin alphabet. There are some minor differences. There are some like variations of certain characters. Same with the German language, right? And we have a Cyrillic alphabet, right, in the Russian part of the world, right, the former Soviet Union and related countries. So the languages might be a bit different, but they use the same writing system. Another fact is that certain East Asian countries, especially after the colonial rules by the British, they started adapting the Latin alphabet to write their language, right? So that's why it's important to understand the writing system and languages are two different things. What we can encode is the symbols that are used in the writing system. So Unicode supports those different characters in writing systems. Right. So Unicode supports a large number of writing systems, including Sinhala text and Tamil text, the script. Right. So for Sinhala language, the allocation of Unicode is starting at 0D80 until 0DFF. This is the Unicode value, and different Unicode values code for a certain character of the Sinhala script. For example, A. Right? It's represented by the Unicode value 0D85. Right? 0D8 is the column number and row 5. 0D85 is A in the Sinhala script. Right? So ver is 0DC0. Right? 0DC column 0. So like that, right? So this is the range, and as you can see, there are some still room for adding new symbols, right? So in the space that's allocated for Sinhala script, we still have some empty slots. So if there's a need for a new character, we can still accommodate them. Now let's look at how Tamil characters, or at least some of the Tamil characters, are represented in Unicode. So in the previous slide, we only saw a part of the Sinhala characters. Right here, we all see part of the Tamil characters. The whole range is for Tamil is from 0B80 to 0BFF. Right? That's the whole range allocated in Unicode for Tamil script, for Tamil characters. Similarly, let's look at a couple of examples. So the letter R, right? It's in 0BB0, column 0BB, row 0. So the code is 0BB0 for R. Yeah, similarly for L, it's 0BB2, right? 0BB column and 2, right? 0BB2. So like that, right? For various writing systems, we have the Unicode allocations for that. There's a range allocated for these languages, along with some empty slots for any potential new coming symbols for that particular language. Let's now look at some Python examples in terms of printing Unicode numbers, right, and printing what the code value is, the Unicode value is. So first we have the CHR method, the built-in function. Probably you remember, this gives the Unicode symbol or character represented by this input Unicode value, right? For this value, what's the character or the symbol in Unicode? So we now try this. So is 0x stands for hexadecimal, so we are giving a hexadecimal number as input. 0D86 is the code. Probably you remember from the table that we saw, it stands for R, right? The Sinhalese character. So when you print S, we see R. Okay, that's using CHR. Then with ORD or ORD, this will return the decimal value of a given Unicode character, right? So decimal value of the Unicode code value, right? So we give the argument a character, a Unicode character. Then with ORD, we can get the decimal, corresponding decimal value of that, and then we can convert it into hex with this hex function. And this is printed here. We have 0x, which says hexadecimal, and D86. So just note that here we had the 0, the leading 0. We don't have it. That's not a problem. But this is hexadecimal D86. To print a Unicode character, we can, so instead of using CHR, we can directly type the Unicode like this. So print, so U, we are saying it's going to be a Unicode value, and this escape symbol with U also tells it that we are passing a Unicode value, and the actual Unicode value is 0BB2, right, which corresponds to the letter L in the Tamil script. This brings us to the end of lecture 7, data representation. To summarize what we did, we first looked at the terms, right? Then we looked at different units of data. We talked about kilobyte, megabyte, right, kibibytes. Remember the difference between taking the 10 to the power 3 versus 1024, right? That gives rise to slightly different units of data. Then we looked at number systems. We looked at decimal, binary, octal, and hexadecimal. We looked at how to convert among these number systems, right? How to convert from decimal to binary and vice versa, and among other number systems as well. Then we looked at representation of numeric data, mainly integers and non-integers. That included floating point numbers, right? So we talked about the 2's complement, right? And finally, we looked at the representation of non-numeric data, mainly textual data. And we talked about the ASCII representation and then Unicode representation, which is widely used nowadays to represent all sorts of characters in a large number of writing systems in the world, right? Beyond just writing systems, beyond languages, we have scientific symbols, mathematical symbols, so on. Right, so apart from the lecture videos and slides, please also go through the lecture notes, because those lecture notes relevant to this lesson as well as other lessons contain very valuable information.